Let's think about these questions. You might want to pause the video and take a look at these questions. Do you know how to answer these questions? Can you answer these questions without a calculator? Obviously, you could figure out the answers to these questions using a calculator, but it's good to be able to answer the questions without a calculator. For one thing, some professors don't let you use a calculator on exams. Also, there's some standardized tests like the MCAT where you can't use a calculator. And maybe most important, you will get a deeper understanding of sine and cosine if you understand the way to answer these questions without a calculator. So, in this video, we're going to learn how to answer these questions and a few more without a calculator. And we're going to do that by using the unit circle interpretation of sine and cosine. Okay, so do you know what is a unit circle? By the way, each time I ask a question in this video, I hope that you'll try to come up with an answer so that you're participating in the video. Unit circle is a circle with a radius of 1. That is, it has a unit radius. That's why it's called the unit circle. So let's say that this is a picture of the unit circle. If that's the case, what would be the length of this line? Well, this is a radius, so it would have a length of 1. And what's the length of this line? That's another radius, so it would also have a length of 1. So a unit circle is a circle where the radius has a length of 1. So now we're ready now for the unit circle interpretation of sine and cosine. So what is the unit circle interpretation of sine and cosine? Have you heard that interpretation? Do you know what that is? Here it is. So in this interpretation, the cosine of an angle is the x-coordinate of the point on the unit circle that corresponds to that angle. And the sine is the y-coordinate of that point. So the basic idea here is that cosine represents an x-coordinate on the unit circle, and sine represents a y-coordinate on the unit circle. For example, let's say we were considering, say, this angle, theta. So if we're considering this angle, theta, what would cosine theta be and what would sine theta be? Can you find them on this unit circle? Can you find those on this unit circle? Can you graph these? Again, I hope you'll pause the video and try to answer each question that I ask. Well, we want to find the point on the unit circle that corresponds to theta. So here's the point on the unit circle that corresponds to this angle, and that point has coordinates. You should know that the first coordinate that you write is the x-coordinate, and the second coordinate you write is the y-coordinate. That's the standard way to write coordinates. And we just learned that the x-coordinate represents the cosine of theta, and the y-coordinate represents the sine of theta. Okay, so that gives us one particular interpretation of sine and cosine. So for example, for this angle theta, would you say the cosine is positive or negative? Would the cosine of this theta be positive or negative? Well, the x-coordinate here is negative, therefore the cosine is negative. And would you say that the sine of this angle theta is positive or negative? Well, again, the y-coordinate of this point is negative. These are our positive directions, and therefore the sine of this angle is also negative. So that's an illustration of how we can interpret the sine and cosine of any angle as the x and y coordinates on the unit circle. And you can see one thing that you can quickly get from that is that it allows you to predict whether any particular sine or cosine is going to be positive or negative. Please pause the video and try this problem. Well, first of all, we have to find an angle of 170 degrees, and that would be approximately, say, over here. Notice that in this interpretation, we measure the angles counterclockwise with the positive x-axis, counterclockwise from the positive x-axis. Well, here's our positive x-axis, and counterclockwise from there is in this direction. So that's where we found the 170 angle. So that means we're focusing on this point. And we know again that the x-coordinate of that point will be the cosine of 170 degrees, and the y-coordinate of that point will be the sine of 170 degrees. So we can say the x and y coordinates of this point will be the sine, the cosine, and the sine. Now, what good is that? Well, one thing is that it allows us to make a prediction. So we can predict, you can see the x-coordinate here will be negative. And we can predict that the sine, the y-coordinate, will be positive. So even without using our calculator, you could confirm, you might want to confirm this on your calculator, but you can see that the cosine is negative and the sine is positive. Actually, don't use your calculator just yet, because we can do something else. We can actually approximate how big these are. What's the actual number for the cosine, and what's the actual number for the sine? You might want to pause the video and ask yourself how you can approximate them. Well, notice that this point is pretty close to this point. This is the point for 180 degrees. 170 is not that far from 180. Well, do you know what the coordinates of this point are? What are the coordinates of this point? We should know its x-coordinate is -1 and its y-coordinate is 0, right? This is the point -1, 0. But doesn't that tell us that the cosine of 170 degrees is just is close to -1? It would actually be technically a little bit bigger than -1. It'll be something like, I don't know, negative 0.9 approximately. So that's on the number line, this is considered to be bigger than -1. And how about the sine of 170 degrees? Well, you can see that's going to be pretty close to 0. This y-coordinate is pretty close to this y-coordinate, so this will be pretty close to 0. It'll be a little bit bigger than 0. So this sine here would be a little bit bigger than 0. And again, you can try to confirm that on your calculator. Okay, so we can see some advantages here to using the unit circle approach. Again, this gives us a deeper insight into what the cosine of 170 and the sine of 170 means. It allows us to predict whether they'll be positive or negative, and it even allows us to kind of approximate what their numerical values would be. Pause the video and try to answer these questions. Well, first of all, we have to find 90 degrees on our unit circle. So the 90-degree angle would be like this. That would be 90 degrees. So this would be the point that we're focusing on. Now, the x-coordinate of this point is 0. So the cosine there is 0. And the y-coordinate of this point is 1. So the sine is 1. So we know that the cosine of 90 is 0 and the sine of 90 is 1. So in this case, we were able not just to not to approximate the answer, but actually to figure out the exact answer using our unit circle approach. Again, you could try confirming these answers on your calculator. Make sure your calculator is in degrees mode, and then you could check whether these answers match what you get in your calculator. I'm pretty sure they will. Okay, so let's try another example. Pause the video and figure these out. Well, can you find 0 degrees? So the angle is supposed to be measured relative to the x-axis. So if we're at an angle of 0, doesn't that mean that we're on top of the x-axis? So this is the point that's at an angle of 0 with the x-axis. At an angle of 0 with the x-axis is just a nerdy way of saying that it's right on the x-axis. And what's the x-coordinate of this point? 1. That's the cosine. And what's the y-coordinate of this point? 0. So that's the sine. Okay, so now we've worked out some further exact values. Pause the video and try to work these out. Now 180 degrees would be this angle. So that would take us to this point. I think we already talked about this point. This point has an x-coordinate of -1. And I tried to kind of trick you here by switching the positions of the sine and the cosine. I hope you didn't fall for that trick. So the cosine here, the x-coordinate would be -1. So here's the x-coordinate, -1. And the y-coordinate here would be 0. So now we figured out the cosine and the sine of 180 degrees. I rearranged them so they follow the earlier pattern, so it's easier to compare our values for each of those. Pause the video and answer this. Well, 360 degrees, if you start at the x-axis and you go 360 degrees, don't you end up back at the x-axis? So 360 degrees is this same point. 360 degrees from the x-axis. 360 degrees from the x-axis is again a nerdy way of saying that it's right on the positive x-axis. So it's the same point here still. So we should get the same answer as for cosine 0. The x-coordinate here is 1 and the y-coordinate here is 0. So you can see from the unit circle approach, the lesson from the unit circle approach is that cosine and sine are what are called periodic functions. Their values repeat every time you increase the input by 360 degrees. Anytime you take an input and you increase it by 360 degrees, you get back to the same angle on the unit circle, and so you're going to get the same answers. This helps us to understand why sine and cosine are periodic functions that repeat every 360 degrees. For example, if you took 90 and you added 360 to it, 360 plus 90, what's that, 450? So what's the cosine of 450? It must be the same as the cosine of 90, 0. And what's the sine of 450? That must be the same as the sine of 90, which is 1. You can check that on your calculator. So from the unit circle approach, we get this deeper understanding of why sine and cosine are periodic functions. Pause the video and see if you can answer this question. Do you know how to interpret radians? I'm actually not going to go into too much detail about radians right now, because radians are usually, I'm intending this video for people who are pretty early in their physics class, and usually radians are not too important until a little bit later in your class. But maybe you know that 2 pi radians is the same angle as 360 degrees. I hope you remember from high school that 2 pi radians is the same angle as 360 degrees. So if you know that 2 pi radians is 360 degrees, then you should know that this row and this row should be the same. So 2 pi radians would again take you 1 full circle back to this point. So the cosine here would again be an x-coordinate of 1, and the sine here would be a y-coordinate of 0. So you can also use, if you understand radian measure, you can also use the unit circle approach to find sine and cosine there. So again, in terms of radians, sine and cosine are periodic functions. Every time you increase the angle by 2 pi radians, you get back to the same sine and cosine. Okay, now there's one more useful trig function that we use a fair amount in physics, which is tangent. So what's the unit circle interpretation of the tangent? Well, we don't really exactly have a unit circle interpretation of the tangent, but there is a way to think about the tangent that's useful when you're using this approach. So let's move on to that. Do you know what the tangent is in terms of sine and cosine? Do you know what tangent is in terms of sine and cosine? You might have learned in high school that the tangent is the sine of an angle is the sine of the angle divided by the cosine. So this is just a true fact about tangent. This is a true fact about tangents. And there's a bunch of places where this is useful in your physics class. You should probably just memorize this fact. It's not directly related to the unit circle, but we can combine it with the unit circle to figure out some interesting things about tangent. So for example, please pause the video and figure out what's the tangent of 0. Give that a shot. Well, remember an angle of 0 degrees would put us here. And the coordinate here is 1, 0. So remember, the tangent of 0 would be the sine of 0 divided by the cosine of 0. But the sine is the y-coordinate here, which is 0. And the cosine is the x-coordinate here, which is 1. So we just figured out the tangent of 0 is 0. The tangent of 0 is 0. You could confirm that on your calculator. Okay, so you can also use the unit circle to figure out some tangents, if you remember that tangent is sine over cosine. So you could say that the tangent of 0 is the ratio of the y-coordinate to the x-coordinate. If you really wanted to give it a unit circle approach, you can say tangent is the ratio of a y-coordinate to an x-coordinate on the unit circle. Well, the ratio of this number to this number is 0. Please pause the video and try this problem. Well, 90 degrees would take us to this point, and you should know the coordinates of this point are 0 and 1. Remember, when we write coordinates, we always write the x-coordinate first and then the y-coordinate. So the tangent of 90, according to our rule, that would be the sine of 90 divided by the cosine of 90. Well, the sine here is the y-coordinate, which is 1, and the cosine here is the x-coordinate. Do you know what this division is? Well, remember, you can't divide by 0. You can't divide by 0, so this is undefined. So what would happen if you try this on your calculator? Your calculator would give you an error message. If you try to find tangent 90, you can check that on your calculator. All right, so we just learned that tangent of 90 is undefined, which is something you might not have realized. Sine and cosine are defined at 90, but tangent is not. By the way, I noticed that some students get these two situations confused. I think students know that some students think that you're not allowed to put the 0 on the top of the fraction, but actually this is fine. It's totally okay to have 0 on the top of the fraction. It's okay to divide into 0. You just can't divide by 0. So this is defined, it's 0, and this is undefined. You can check that on your calculator. Let's do another, see if you can figure out the tangent of 180. I hope you gave that a shot. Well, 180 degrees would be this angle. That would take us here, and the coordinates of that point, the x-coordinate is -1, and the y-coordinate is 0. And according to our rule, tangent is the sine of 180 divided by the cosine of 180. So it's the y-coordinate, which is 0, divided by the x-coordinate. And remember, this is not undefined. It's okay to have a 0 on the top of the fraction. This is just 0. Okay, I guess we could consider a few other possibilities. So for example, let's say you were going to do the tangent of 100 degrees. And just predict, should this be positive or negative? Would you predict that the tangent of 100 degrees would be positive or negative? Well, 100 degrees would take us to, say, around here. You can see that this is going to have one negative coordinate and one positive coordinate, right? The x-coordinate will be negative and the y-coordinate will be positive, so we can predict that the tangent of 100 degrees would be negative. So that's another example of the type of interpretation and understanding that we get from using the unit circle approach. Please pause the video and try this problem. Well, I hope you tried to figure this out by using a unit circle. So they tell us here that theta is an acute angle, and that means that theta is in what's called the first quadrant. Theta is around here. For example, we know theta is not like this, because that would be bigger than 90, and that's not an acute angle. An acute angle is an angle that's less than 90. So to be an acute angle, we should be in this quadrant. And then what happens when we increase theta? Well, if we increase theta, doesn't that mean that we're going to move in this direction on the unit circle? For example, we might move from here to here. And remember that the x-coordinate of this point is the cosine, and the y-coordinate of this point is the sine. Well, if we increase theta, doesn't that mean we're going to move to a smaller x-coordinate? When we increase theta from here to this bigger angle, the x-coordinate decreases. And doesn't that mean that the cosine will decrease? Because the x-coordinate, the cosine is the x-coordinate. So we just saw that for acute angles, the angle theta, the input and the output of cosine move in opposite directions. When you increase the angle, you decrease the cosine. There's quite a few places in physics where it's really helpful to understand that increasing theta decreases the cosine. Why are we focusing on acute angles? Well, the large majority of the angles you're going to deal with in physics will be acute, less than 90. The great majority of the angles you deal with in physics will be less than 90, so that's what I'm going to focus on in this part of the video. I think you can see that you could also predict how changing theta would affect cosine if you had an angle that was bigger than 90, or bigger than 180 even, or bigger than 270. This is 270 even. But for physics purposes, it's most useful to focus on acute angles that are less than 90. Now I added an additional question. Pause the video and answer this question. Well, I really already did a lot of the work on that for you. Increasing theta means, again, that we're moving from this angle to this angle, from here to here. And you can see this point has a greater y-coordinate than this one. So if we increase theta, that would give us a y-coordinate on the unit circle. That is bigger than the one we had before. From here to here is a bigger y-coordinate. And doesn't that mean that the sine of theta, therefore, would get bigger? So you can see that for acute angles, again, we're assuming it's an acute angle, less than 90 for an acute angle, when you increase theta, you increase the sine of theta. So you can see the pattern is quite different for sine and cosine. This is useful enough that you might want to memorize it, but if you forget the pattern, you should be able to quickly figure it out using the unit circle approach. I've added one more question. And again, I'm still supposing it's an acute angle. So if we suppose we have an acute angle, how would you answer this question? I hope you paused the video and actually tried to come up with an answer for that. Well, remember that the tangent of theta is the sine of theta over the cosine of theta. Now we know that when theta increases, we know the sine of theta goes up. We already figured that out. But the sine of theta is on the top of this fraction. When you make the top of the fraction bigger, the whole fraction should be bigger. So the tangent of theta should also get bigger. That's a pattern that works when all the numbers are positive, and all the numbers will be positive in this first quadrant. Now, there's something you should worry about, because changing theta will also change the cosine. How will changing theta change the cosine? Well, we already figured that out. If we increase theta, the cosine is going to go down. Now the cosine is on the bottom of the fraction. What happens when you make the bottom of a fraction bigger? Smaller. Well, if you make the bottom of the fraction smaller, that actually makes the whole fraction bigger. When the bottom of a fraction gets smaller, the whole fraction gets bigger. I covered those types of ideas in an earlier video series called something like Understanding Equations, How to Understand Equations. So if you're not familiar with these ideas, you might want to look at that earlier video series on Understanding Equations. But anyway, we've seen that the whole fraction will get bigger, and that's represented by the tangent. So we can see that fortunately the way that theta affects the sine will ultimately have the same effect as the way it affects cosine. If we increase theta, the top of the fraction will get bigger, which makes the tangent bigger. And if we increase theta, the bottom of the fraction will get smaller, which also increases the tangent. So both of those give the same prediction. So our overall prediction is that when theta increases, the tangent of theta will also increase. That's for acute angles. Notice how I worked this out by writing down each little thought step. This is a real useful technique when you're trying to work things out in math and physics. Don't try to do the steps in your head. Try to write down each of the thought steps down on paper. Okay, so now we figured out all the patterns for acute angles. Sine, so when you increase theta, that increases the sine and it increases the tangent, but it decreases the cosine. You can kind of remember that because notice that in this equation, sine is on the top. So you can see that if you increase the sine of theta, it's not surprising that would also increase the tangent of theta. Okay, so now anytime you want to know how changing the input will change the output for sine, cosine, or tangent, we've shown how you can figure that out using the unit circle approach. And I hope, again, this gives you a deeper understanding into these functions. Please pause the video and try to work out this problem. Do you understand what this question is asking? So what I'm asking is what's the smallest that cosine theta could ever be on the number line? And what's the biggest that cosine theta could ever be? Does cosine theta say, is it going to be between, I don't know, 0.2 and 6? Or is it going to be between -8 and 32? What's the lower bound and the upper bound on the number line for cosine theta? Well, I hope you'll pause the video and give that a shot. All right, I hope you did that and paused the video and gave that a shot. And now let's try to work through that together. Well, obviously I intend you to figure this out using a unit circle approach. Now, remember the cosine theta is the x-coordinate on the unit circle. So this is really asking what's the range of x-coordinates on the unit circle? Well, can't you see that this point over here has the lowest x-coordinate on the unit circle. This has an x-coordinate of -1. So the smallest x-coordinate we can have on the number line here would be -1, and the biggest x-coordinate would be at this point, which is an x-coordinate of 1. So all the x-coordinates are going to be between -1 and 1. So we can say that this is the range of the outputs for cosine theta. Actually, I should say it's less than or equal to 1 and greater than or equal to -1, because it can equal those. Boundary points. The cosine of 0 would be 1, and the cosine of 180 would be -1. So this is the range of outputs for cosine theta. So, for example, could you ever have, say, the cosine of theta equal to 7? You probably, I think a lot of students don't realize that this doesn't make any sense. This is impossible. It's impossible for this number to be 7 because that's outside the x-coordinates that are possible. Could you have, say, -1.2? Nope, that's impossible because you don't have any x-coordinates of -1.2 on the unit circle. So that's something I think a lot of students don't realize, that the outputs for cosine always are between -1 and 1. By the way, don't confuse the inputs and the outputs. It's totally okay for the input to be bigger than 1. We could totally have an input that's bigger than 1. What we're saying is that the outputs have to be between -1 and 1. You can really have any input you want because you can measure any angle that you like on the unit circle. You can even measure negative angles if you think about moving in this direction. So the inputs to the cosine could be any number, but the outputs have to be between -1 and 1. Okay, so that's some more insight that we would not have been able to get without our unit circle approach. A new question, please pause the video and try to answer this question. Well, remember the sine is the y-coordinate. Well, the least y-coordinate on the unit circle is the y-coordinate here, which is a y-coordinate of -1. And the greatest y-coordinate is the y-coordinate here, which is a y-coordinate of 1. So the range of the sine is between -1 and 1. The same as for cosine. So for example, could you have a sine of 1.4? No. You can't have an output of 1.4. It has to be between -1 and 1. So that would not make sense. So the range of the cosine is the same as the range of the sine. That doesn't mean that these equal each other. They don't equal the same value, but they have the same lower bound and the same upper bound. Pause the video and try this problem. This is considerably trickier than the other ones, but we should remind ourselves that tangent theta is sine theta over cosine theta. Well, for example, we already know what's the tangent of 0. That would be this point. We've already learned tangent of 0 would have a y-coordinate of 0. If you put a 0 on the top here, you would get 0. We know the tangent of 0 is 0, so we know that 0 is in the range. And then what happens as we increase the angle in this direction? What happens as we increase that angle? Well, as we increase theta, we know that cosine of theta is going to get close to 0. As theta gets close to 90 degrees, the cosine will get close to 0. That means we're going to be putting a very small number here on the bottom of this fraction. But if you put a very small number on the bottom of the fraction gets bigger and bigger and bigger. So as theta gets close to 90, and the denominator gets closer and closer to 0, the tangent of the theta is going to get bigger and bigger indefinitely. So what that basically means is there's no upper limit on the tangent. There's no upper limit on the tangent. You can make it as big as you like. So a mathematician would say that it goes to infinity. That just is a fancy way of saying there's no upper limit on the tangent. Again, do you see why that is? So as we go to this point over here, the numerator is getting close to 1, but the denominator here is getting very close to 0. So we're putting a very small number on the bottom of the fraction. And as the bottom of the fraction gets smaller and smaller and smaller, the whole fraction will get bigger and bigger. It'll get as big as you like. Let's just spell out that logic a little bit more precisely here. So the logic again is that as this angle gets very close to 90 degrees, we know that cosine of theta, the x-coordinate, is going to get very close to 0. As the angle gets close to 90, the x-coordinate on the unit circle gets close to 0. At the same time, when the angle gets close to 90, sine theta, the y-coordinate, gets close to 1. These points have a y-coordinate that's close to 1. Well, if the bottom of the fraction is getting close to 0, while the top of the fraction is getting close to 1, then the fraction as a whole will get really big. And it'll get bigger and bigger the closer the angle gets to theta, and the closer the bottom of the fraction gets to 0. You could check that on your calculator, and you can see that if you put in a tangent of, say, 89 or 89.9 or 89.99 or 89.9999 degrees, the tangent gets bigger and bigger. All right, and what about, say, if we considered, say, this point here? Well, at this point, we would have the sine of theta, that would be just a little bit less than 1, and we would have a cosine of theta that is negative and close to 0. So this would be an x-coordinate like negative 0.1 or negative 0.01, negative and close to 0. So if, again, we're going to be dividing by a number that's very close to 0, so that's going to give us a very big negative value. So if you take angles that are a little bit bigger than 90, you get huge tangents, very positive tangents. And if you take an angle that's just a little bit more than 90, like 90.1 or 90.01 or 90.001, then you're going to get an extremely negative tangent. So the tangent really fluctuates between negative infinity and positive infinity. That basically means that tangent can be any number. There's no limit on the tangent. So could you have a tangent of 22? Yes, that's fine. You could have a tangent of 22. Can you have a sine of 22? No. Sine can't be bigger than 1, but tangent can be bigger than 1. Tangent can be any number, but sine and cosine have limits. Okay. There's no limits on the tangent, but there are limits on the range of the sine and the cosine. I went through this one a little bit quickly because it's useful if you know the range of the tangent, but the ones that are most useful are sine and cosine. So if you found what I just covered to be a little bit confusing, you could just focus on making sure you know the range of the sine and the cosine. Those are the ones that are going to be most useful to you in your class. I know that the logic for this one was a little bit more complicated. I went through it a little bit quickly because it's not the most important thing in your physics class, although it's some useful background information. Okay, so the most important thing we went over here are the range for the sine and the cosine. And if you ever figure these out, you could figure them out for the unit circle. The outputs for sine and cosine have to be between -1 and 1. And again, remember, that's not telling you the inputs. The inputs for sine and cosine could be any number. The inputs for sine and cosine could be any number, but the outputs have to be between -1 and 1. We know that the inputs for tangent can't be any number. Tangent is not defined, an input of 90, say. But the input for sine and cosine could be any number. Okay, now I hope you can see that you could use this unit circle approach to figure out the shape of the entire graph for sine, cosine, and tangent. You could figure out what the graph of sine, cosine, and tangent look like for any angle by thinking about how sine, cosine, and how the coordinates change as you move around the unit circle. One thing you should already know is that the graphs are periodic. For example, we know that the graphs for cosine and sine should repeat themselves every 360 degrees. So you could use this unit circle approach to figure out the graphs for sine and cosine. And for tangent, I'm not going to do that right now because I'm intending this particular video to be something that you can watch early in your physics class to help you with what you need to know early in the physics class. And you don't really need to understand the entire graph of sine and cosine and tangent early in your physics class. Later, at a later point in the physics class, say when you start working on waves and oscillations, it can be quite useful to understand what the graph of sine and cosine look like. If you want to challenge yourself, you might try to figure out what the graphs of sine, cosine, and tangent look like using the unit circle approach. You could easily check your work by looking up those graphs online. But I'm not going to go into those details, like I said, right now, because that's not something you'll need. That's going to be too important for you early in your physics class. All right, instead, let's go on to this. Pause the video and try to answer this question. All right, I hope you gave that a shot. We'll use our unit circle approach. So first of all, we want to find 30 degrees here on the unit circle, and that would look say like this point. All right, the key point is to see that this angle 30 is closer to the x-axis than to the y-axis. For example, would this be a good way to draw 30? I think that's pretty clear this is not 30. It might help you to see, of course, this would be an angle of 90. Halfway to 90 would be 45. So this is less than halfway to 90. 30 is less than halfway to 90. So it should be closer to the x-axis than to the y-axis. Now remember that our friend here remembered that the coordinates are 1/2 and √3/2, but he couldn't remember which was which. Well, first of all, which is bigger, 1/2 or √3/2? I hope it's obvious that √3/2 is bigger than 1/2. If that's not obvious, remember that 1/2, that's the same. 1/2 is obviously the same as √1/2, and it should be obvious that that's less than √3/2. So clearly 1/2 is the same as the root of 1/2, and now you can easily compare these and see that √3/2 is bigger than this. So √3/2 is bigger than 1/2. Well, which should be bigger here, the x-coordinate or the y-coordinate? You can see just from looking at it that at this point the x-coordinate is bigger than the y-coordinate, right? You can see from looking at it that this distance, the x-coordinate, is bigger than this distance. So the bigger number has to go with the x-coordinate. So I'll put the bigger number here with the x-coordinate and the smaller number here with the y-coordinate. So if you can remember that the cosine and sine of 30 involve 1/2 and √3/2, then you can easily figure out which is which by knowing that on the unit circle, the x-coordinate here should be bigger than the y-coordinate. So we can say that the cosine of 30 degrees is the x-coordinate, √3/2, and the sine of 30 degrees must be the y-coordinate, 1/2. At 30 degrees, we'll have a bigger x-coordinate than a y-coordinate. These are values that come up quite a lot on problems. These values come up a lot on problems, so it might be useful to be able to remember them or to figure them out using this approach. Pause the video and try this problem. Well, the key thing to realize is 60 degrees would be something like this. This would be an angle of 60 degrees. And isn't an angle of 60 degrees, do you see that that's going to be, just like this was 30 degrees from the x-axis, this is 30 degrees from the y-axis, right? 60 degrees is 30 degrees from the y-axis, because 60 and 30 is 90. So what we can figure out here is that these coordinates should be symmetric with these coordinates. I don't know if I quite drew them symmetrically here on the picture. Maybe they should be a little bit further down. But anyway, this angle here with the x-coordinate should be the same as this angle with the y-coordinate. These should be symmetric. So these coordinates just flip. This will be 1/2, and this will be √3/2. And I think you can clearly see here that at this point, the y-coordinate, from the picture, the y-coordinate should be bigger than the x-coordinate. And that's consistent with these numbers. The y-coordinate is bigger than the x-coordinate. So that tells us that the cosine of 60 is the bigger coordinate, the smaller coordinate, 1/2. And the sine of 60 is the bigger coordinate, √3/2. So I'm going over this because cosine and sine of 60 and 30 degrees, these are values that come up a lot that some professors might kind of expect you to have memorized. And you can kind of see how you can use the unit circle approach to help you remember which one is √3/2 and which one is 1/2. This method only works if you know that √3/2 is bigger than 1/2. But if you do, then you can just figure out which should have the bigger x-coordinate and which should have the bigger y-coordinate. And what can you predict about these? Well, the key thing is that 45 degrees is halfway between the x and the y coordinates. 45 degrees is half of 90. So what I was hoping you would predict is that the cosine of 45 should equal the sine of 45. You can predict that cosine of 45 should equal sine of 45 because of symmetry. So this angle, 45 degrees, would be exactly halfway between the two axes. This would be our 45-degree angle. And because of symmetry, this should have the same x and y coordinates. So you could predict here that the cosine and the sine should be equal. This is another one that some professors might expect you to have memorized, or that you might need to have memorized for the MCAT. So, or that might just be useful to know. So let's build that in. So it turns out that these coordinates are square root 2 over 2. And what should this coordinate be? Well, because of symmetry, it should be the same also. Square root 2 over 2. It actually wouldn't be that hard to use the Pythagorean theorem to figure out these numbers, but I'm not going to go into that. And does that make sense? So you should be able to see here that 1/2 is the same as square root 1 over 2. And clearly that's less than square root 2 over 2. And clearly that's less than square root 3 over 2. So you can see that this is the smallest of the three numbers, then this is in the middle, and this is the biggest. And you can see that from the picture. Here we have the smallest y-coordinate of 1/2, then a bigger y-coordinate of root 2 over 2, and the biggest y-coordinate of root 3 over 2. Or here we have the smallest x-coordinate of 1/2, and here there's a bigger x-coordinate of root 2 over 2, and there's the biggest x-coordinate of root 3 over 2. By the way, like I said, I didn't figure out these numbers of root 2 over 2. I didn't figure them out. I just said that you might have memorized that the numbers are root 2 over 2, but it should make sense that they're equal. Like I said, if you want to figure them out, you can figure them out pretty easily using the Pythagorean theorem if you know that the x-coordinate and the y-coordinate are equal here, but I won't go into that. So anyway, now we know that the cosine of 45 is root 2 over 2. And the sine of 45 is root 2 over 2. Like I said, I didn't prove that these are the right numbers, but I did prove that they should be the same numbers for sine and cosine. And it should make sense that it's root 2 over 2, because that's between root 1 over 2 and root 3 over 2, which were the numbers we used for these. Okay, so anyway, cosine and sine of 30, cosine and sine of 60, cosine and sine of 45, these are pretty common values that might be helpful for you to memorize or to be able to figure out. And if you forget them, you can kind of use this unit circle approach to figure them out. You could make this very picture right here. It shouldn't be too hard to make this very picture and to figure out where we use root 3 over 2, where we use root 2 over 2, and where we use 1/2 in the patterns. So that's just one more way in which knowing about the unit circle can be helpful to you for understanding sine, cosine, and tangent. I guess now we may as well figure out what's the tangent of 45 degrees. Pause the video and determine what's tangent of 45 degrees. Well, you don't need to have any of the stuff that we talked about so far memorized in order to figure this out. Tangent of 45 degrees would correspond to this point. Remember that the tangent is sine divided by cosine. Well, that would be the x-coordinate divided by the y-coordinate. Well, again, because of symmetry, it should be obvious that the x and the y-coordinates are equal for this tangent. So it should be obvious here that this would be sine of 45 degrees over cosine of 45 degrees. And because of the symmetry, since 45 degrees is halfway between 0 and 90, the x-coordinate and the y-coordinates would be the same. The sine and the cosine would be the same. And when you put the same number on the top and on the bottom of a fraction, you get 1. So the tangent of 45 would be 1. Of course, now we know the specific values. So if you put root 2 over 2 on the top here, and you put root 2 over 2 on the bottom, clearly they cancel and you would get 1. So it should be clear to see here the tangent of 45 is 1. If you want to, you can also figure out the tangent of 30 degrees and the tangent of 60. To do that without a calculator, you have to be comfortable with dividing fractions. So if you'd like a fun activity, you can try to figure out the tangent of 30 degrees and the tangent of 60 degrees. But I won't go into that right now. These are the values that are most likely to be the most useful to you in your physics class. There's one more thing I wanted to cover. There is something that might have been worrying you in this video, which is that this video seems to contradict something else you might have learned about sine and cosine and tangent. So you should already have learned Sohcahtoa. From Sohcahtoa, you know that the sine is the opposite side over the hypotenuse of a right triangle, and the cosine is the adjacent over the hypotenuse side, and the tangent is opposite over adjacent. Well, doesn't that contradict what we learned in this video? In this video, we learned that sine is a y-coordinate on the unit circle, and cosine is an x-coordinate, and then tangent is sine over cosine. Those seem like two contradictory approaches. Well, they're not contradictory, they're just alternative. They both turn out to mean the same thing. So there's no contradiction between Sohcahtoa and the unit circle. Both Sohcahtoa and the unit circle approach are correct. They're both correct, and they both imply each other. So the last thing I wanted to do is just show you or help you to see that Sohcahtoa is really the same thing as the unit circle approach, looked at in a different way. So you might, so we're going to do a little proof here to show that Sohcahtoa implies the unit circle approach we've been talking about. This is not something that you're likely to be tested on directly in your physics class. I'm just covering this to help you have a better understanding of sine and cosine. But if you're not interested in seeing this relationship, you could certainly skip this part of the video. This is a very simple proof, but if you're not interested, you could skip it. Okay, so anyway, let's. I hope that you paused the video and tried to come up with an answer. This is not the kind of thing you should spend a very long time on, like I said, because it's not going to be tested directly in your physics class, but it turns out to be pretty easy to see the relationship here. Okay, so let's look at a unit circle, and we wanted to consider an acute angle theta. So that just means that it's in this quadrant. So I'll look at an angle like this. And now I'm going to say, so we know that this has an x-coordinate. We'll call this x-coordinate just x. We'll say x and y are the x and y coordinates here. Now, should we say that the x-coordinate is the cosine of theta? And should we say that the y-coordinate is the sine of theta? Well, normally that would be a great thing to do, but we definitely should not do that on this problem. And the reason is that on this problem, we're trying to prove that the cosine is the x-coordinate, and we're trying to prove that the sine is the y-coordinate. Well, we can't prove it if we just assume it, so to speak. We can't use the idea that cosine of theta is x to prove the idea that cosine of theta is x. That would be circular, so to speak. All right, so ordinarily, on any ordinary problem, it would be a great idea to say that the cosine represents the x-coordinate and the sine represents the y-coordinate. But that's not how to proceed in this proof. So what are we allowed to use and assume? Well, the problem told us we're allowed to use and assume Sohcahtoa. So we will use and assume the ideas behind Sohcahtoa. Use and assume these ideas, and hopefully we will be able to use these ideas to demonstrate at the end of the proof that the x-coordinate is the cosine of theta and that the y-coordinate is the sine of theta. That's what the problem means when it says that we're supposed to use these ideas and show that they imply these ideas. Hopefully, as we proceed through this short proof, it'll become clearer to you how to do that and what this task means. And now I'm going to say, so we know that this has an x-coordinate. We'll call this x-coordinate just x. We'll say x and y are the x and y coordinates here. And let's draw the right triangle since we want to apply this to Sohcahtoa. So if we were going to draw a right triangle, it would look like this. And then what is this distance? Well, you can see that that distance is x, the x-coordinate. The x-coordinate tells us that distance. And what is this distance? Well, isn't that y, the y-coordinate? So this distance is y. Now, in order to use Sohcahtoa, we have to label the hypotenuse, opposite, and adjacent sides. Do you know how to do this? Who's the hypotenuse? Well, this side is the hypotenuse because it's across from the 90-degree angle. And adjacent means adjacent to the angle that we're focusing on. Well, we're focusing on this angle of theta here at the base of the triangle. So this side, this leg, adjacent means the leg that's adjacent to the angle that we're focusing on. And this is the leg that's adjacent to the angle that we're focusing on. Opposite means opposite, the leg that's opposite to the angle that we're focusing on. Well, this leg is opposite to the angle of theta that we're focusing on. That's why it's labeled opposite. And this leg is adjacent to the angle of theta that we're focusing on. That's why it's labeled adjacent. So those are the sides of that represent the hypotenuse, opposite and adjacent sides that we can use as we now apply Sohcahtoa. Now, according to Sohcahtoa, the sine of theta is the opposite side over the hypotenuse. Now the side that's opposite to theta would be y. And how long, where's the hypotenuse? This is the hypotenuse, right? Here's our hypotenuse right here. And how long is this hypotenuse? Well, remember, this is the unit circle. It's the unit circle, so the hypotenuse has a length of 1. So we just proved that the sine of theta is the y-coordinate. Okay, so like I said, there's no contradiction between Sohcahtoa and the unit circle approach. You can see that Sohcahtoa implies that the sine of the angle is the y-coordinate on the unit circle. And you can see the reason why that works is because the unit circle has a hypotenuse of 1. So when the hypotenuse is 1, the sine of theta turns out to be exactly the same as the length of this side, which is the y-coordinate. Cosine of theta is adjacent over hypotenuse. So we have that the cosine of theta, now the adjacent side to theta is x. X is adjacent to theta. And again, the key to the proof is that the hypotenuse is 1. So we can see that, just like the unit circle approach says, the cosine of theta, let's see, really does equal x, which is what we were trying to prove. So the key here again is that the radius is 1. Since the radius is 1, adjacent over hypotenuse is just the length of the adjacent side, and the adjacent side is the x-coordinate. So I think we did what we were trying to do here. We showed that Sohcahtoa implies that the cosine of theta is the x-coordinate, and Sohcahtoa implies that the sine of theta is the y-coordinate. Now we only did that for an acute angle. We did so far the proof doesn't apply to the other quadrants. If you want to give yourself a challenge, you might want to try to extend this proof to the other quadrants. But this should be enough. This should be enough to make it plausible to you. This should be enough to make it plausible to you that Sohcahtoa and the unit circle approach are consistent with each other, and in fact they imply each other. And then finally we could do the tangent of theta. Well, according to Sohcahtoa, the tangent of theta is the opposite over the adjacent. Well, the opposite side of this triangle is y, and the adjacent side is x. But we already figured out that y is the sine of theta, and x is the cosine of theta. So now we've done the proof for part B. We showed that Sohcahtoa implies that tangent is sine over cosine. Okay, like I said, you're not going to be tested on this kind of proof directly, but since you are going to be using sine, cosine, and tangent a lot in your physics course, and maybe in other courses, so it's worth taking some time just to try to get a deeper understanding of sine, cosine, and tangent. So I thought it was worthwhile to see that the unit circle approach and Sohcahtoa are not contradictory. They're just alternative approaches that really imply each other. So they're both correct. And which one should you use? It just depends on what's convenient for the particular problem. Sometimes it'll be more convenient to think about Sohcahtoa. Sometimes it's more convenient to think about the unit circle. Sometimes you want to keep going back and forth in your mind between both approaches. And the purpose of this little proof was just to show you, or just to make it plausible to you that they're not contradictory and that in fact the two approaches imply each other. Like I said, this is not a complete proof that Sohcahtoa is equivalent to the unit circle approach, but it should be enough to make it plausible to you. That Sohcahtoa and the unit circle approach are consistent and really imply each other. And really, again, what it kind of comes down to is the fact that the unit circle has a hypotenuse of 1. That's what allowed these parts of the proofs to go through. Okay, let's wrap up this video by doing a summary. Why don't you pause the video and try to fill in the blanks. Fill in the blanks for this summary. Well, what is a unit circle? I hope that's very obvious by now. It's a circle with a unit radius, a radius of 1. And I didn't mention it, but obviously we assumed that the unit circle here was centered at the origin. So in our unit circle interpretation, we think of a circle with radius 1 centered at the origin. So then what's the unit circle interpretation of these concepts? I hope that was easy for you. We interpret cosine as the x-coordinate, sine as the y-coordinate on the unit circle. And this is not technically about the unit circle, but we saw it was useful to remember that tangent is sine over cosine. And then we can also figure out stuff about tangent from the unit circle. Okay, and then we saw how we could figure out all of these exactly from the unit circle. So did you go through and try to work these all out? Now, I hope you didn't try to answer these from memory. I'm not saying you should memorize these. I'm saying you should be able to quickly figure them out by picturing the unit circle. So I hope you can quickly figure out all of these. That's really, in a way, one of the main goals of this video. My hope is that you can quickly figure out all of these values by mentally picturing the unit circle. Or if you can't quite do it by mentally picturing the unit circle yet, you might have to draw the unit circle to figure them out. For example, an angle of 0 would be right on the x-axis. And that point on the unit circle has an x-coordinate of 1 and a y-coordinate of 0. Or an angle of 90 would be where the unit circle crosses the positive y-axis. And that has an x-coordinate of 0 and a y-coordinate of 1. So we went through how you can figure out all of these from the unit circle and how you can figure out these values by using this formula for tangent. Again, these I was hoping not so much that you would have memorized. I hope that you can figure out why these patterns make sense from the unit circle. When you increase the angle on the unit circle, you go to a smaller x-coordinate. And you go to a bigger y-coordinate. So the sine gets bigger and the cosine gets smaller. And you can also use that to figure out the tangent using this formula. So again, I'm hoping not that you'll really have these memorized, but that you can figure them out, especially cosine and sine, from the unit circle. And again, you should be able to understand these ranges now. The range of x-coordinates on the unit circle is from -1 to 1, and the range of y-coordinates on the unit circle is from -1 to 1. So it should be obvious that these are the range of the outputs for the sine and cosine. Tangent was a little bit more complicated, but we saw that when you think about it, tangent can take on any value. I made a mistake here. I think I had this as maybe sine 30 when I meant sine 60. So I went back and fixed it. So I tried to fill those out. Now what I was hoping here is not that you would, these are not things that you can figure out just from the unit circle, except maybe for this line. But these are values that might be helpful to have memorized, and it helps to remember the pattern if you know the unit circle. For example, we know that as we go from 30 to 60, we expect the y-coordinates to increase. So that tells you the pattern should be smaller number, middle number, bigger number. But if you go from 30 to 60, the x-coordinates should decrease. And that tells you that the pattern is biggest number, middle number, smallest number. So that the unit circle might help you to remember these values, even though it doesn't allow you to figure them out directly, at least for 30 and for 60. Okay, all right. So I hope that you feel now that you have a better understanding of the meaning of sine and cosine and tangent. And the reason why it was worth taking the time to go over this material is because you'll be using sine and cosine at a bunch of different places during your physics class. And most people just kind of punch sine and cosine into their calculator without having any idea what the sine and cosine really means. So I hope that's a shame, since you have to use them so often in your class. So I hope that now when you're punching sine and cosine into your calculator, they won't be quite so mysterious, and you'll have a kind of an idea of what your calculator is really doing. So for example, when you type into your calculator the cosine of 27 degrees, what the calculator is really doing is figuring out what would be the x-coordinate of an angle of 27 degrees on the unit circle. So that should make you feel more comfortable with these concepts. And we also saw there's some specific aspects of the unit circle that give you some techniques that can be helpful, like knowing you can figure out these particular values exactly, or you can figure out how sine and cosine change when you change the angle. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge of $1 or more at my Patreon page. You can visit my Patreon page by clicking the link on the screen or by using the link in the video description box. Thank you.